Вот на твоем ряду стоит голова ближайшая.
Саша.
А что ты можешь говорить?
Темно.
Good afternoon, dear guests, dear colleagues, dear friends. It's my great pleasure to introduce for you our third very honorable guest, Professor Roger Kornberg. Professor Roger Kornberg was born in St. Louis State, Missouri, and he is son of biophysicist Arthur Kornberg, who won the Nobel Prize in 1959. Okay. Roger Kornberg graduated Harvard University in 1967, and he worked as professor of Stanford University from 1978. Professor Kornberg is member of National Academy of Science of USA, and he is a member of American Academy of Art and Science. In 1997, Roger Kornberg became prized by Harvey, and in 2016, Professor Kornberg is Nobel Prize winner in the field of chemistry, and he is also co-chair of Scientist Consultative Council of Skolkovo Foundation. We are very happy to get lecture by Professor Roger Kornberg, and I very glad to announce his lecture, which named as molecular mechanism of transcription. So please, Roger Kornberg.
This is our microphone. This is our microphone. This is your microphone.
So I need to use this
Okay.
one. With this I can be heard.
Yes.
Okay, excellent. So first, my thanks for the invitation. It is a great pleasure to visit. It's a part of the world that I had never seen but often hoped to do, and also a great center for science, which is my principal reason for being here. I'm a great admirer of the history and the tradition of science in Russia in general, in this region in particular, and it is indeed an honor to speak to you today. I will tell you a story, my own scientific story. It took place over a period of about 30 years. I'll only be able to tell you a few of the highlights in the course of some 30 to 45 minutes. I'll be very glad to answer questions and tell you about more detail at the end. I'll begin with a time in the early 1970s when I was about the same age as some of the young people in the audience. And I became interested in the structure of the chromosomes of eukaryotes, including simple unicellular eukaryotes such as yeast, all the way to those of higher organisms, including humans. From a combination of X-ray and biochemical studies, I was led to propose the wrapping of DNA around a set of 8 protein molecules referred to as histone proteins in a unit of structure that is referred to as the nucleosome. This is the basic unit of coiling DNA in all eukaryote chromosomes. It was apparent from the outset, so from the very conception of that idea, that such coiling of DNA would interfere with many DNA processes, including both the replication and also the expression of the genetic information. Some years later, Yali Lort and I could show that coiling DNA in this manner that included the start site, so the beginning of a gene, would prevent its transcription, prevent its expression in a cell-free system. Soon after, it was shown by colleagues elsewhere that such coiling of DNA in nucleosomes would prevent also the expression of the genetic information in living cells, for example, in yeast cells in vivo. From this, we came to understand the nucleosome serves as a general gene repressor. It prevents the expression of the many thousands of genes in eukaryote organisms, except those whose transcription is brought about by specific positive regulatory mechanisms. Much of our work since that time, up to the present, has been devoted to the discovery of those positive regulatory mechanisms. There won't be time to tell you in detail about that research today. I'll summarize only very briefly some of the outcomes. first, it was thought the repression of transcription by the nucleosome was overcome by removal of the histones from the DNA. Evidence for this idea came from the discovery the DNA associated with genes active in a particular cell or cell type of an organism was especially exposed to attack by enzymes that cleave the DNA, known as nucleases, by chemical reagents and so forth. But then, some years later, it emerged that histones are still present, associated with genes active in expression, undergoing transcription. This could be demonstrated with the use of antibodies that would recognize modified forms of the histones. Histones modified by the addition of methyl or acetyl or phosphate or other moieties, especially in what are called the tails of the histones that protrude from the core region of the nucleosome particle. On this basis, it was generally accepted and believed throughout the period of the 1990s and until only a few years ago that histones are not in fact displaced, not removed for genes which are active in expression, active in transcription, but rather in consequence of those chemical modifications, the structure of the nucleosome particle is reconfigured, is altered in some manner that makes it now conducive, now able to be expressed, and also, of course, susceptible to the attack by enzymes and chemical reagents that was observed in the past. It was with the purpose of discovery of this reconfigured or altered structure of the nucleosome that two postdoctoral fellows working with me about 10 years ago sought to isolate and to determine the structure of the altered particle. What emerged from their work I can only summarize briefly. They discovered that both of the previous ideas were partly correct. That nucleosomes are removed, but they are also replaced. They are both absent from, but also present on the DNA of genes undergoing transcription. What they discovered, a more appropriate statement, concerns not the removal of nucleosomes or their presence, but rather a conversion of the chromosomal structure of the gene from a static to a dynamic state upon activation for expression. What they discovered is that nucleosomes are removed, so the histones are taken off the DNA, but also added back. The nucleosomes are rapidly reassembled in the